We have already discussed a few mathematical constants earlier, especially E, phi. E is 2.718, phi is 3.14. So we have discussed a few of the mathematical constants earlier. And we would also be discussing something about the various standard functions which we will be using in various applications in finance and actuaries. The most common functions being e to the power of x, the log x, the the x to the power of a to the power of x, x to the power of n, and we will also talk about the integral value of x, the modulus of x, the minimum and maximum values. These are some of the various aspects, their typical shapes, and for what kind of values they are typically applicable for. Those are some of the most common things we would be discussing as a part of this particular chapter. So, with that basic introduction, let's jump start into our understanding. To start with, we will look at the exponential function, which is typically written as e to the power of x like this, or in some cases, it is also written as exp and in the bracket x. Both of them mean one and the same, it's only the representation that differs. And though the calculus way of expressing e power x is more like this, but I suggest if you can remember this expansion of e to the power of x, which is 1 plus x plus x squared by 2 factorial plus x cubed by 3 factorial and so on, you should be able to answer a decently good number of questions out of this. Now, only thing you need to understand is what is this factorial. Simple way to define the factorial is multiply that number, decrease it by 1 until 1 and put up the value. So 2 factorial means 2 into 1, which will give me 2. 3 factorial will make it 3 into 2 into 1, which will make it to 6. And that's the way you define factorial, and factorials are generally defined only for natural numbers. So decrease those natural numbers one by one until 1, multiply all those numbers, and that is what will bring you the value of that factorial. Now, if you observe this particular graph of e to the power of x, this is the way you see a typical e to the power of x graph. Some of the things you should understand from this graph, because these are the common questions that can get generated for us. As the value of x is increasing, which means e to the power of 1 versus e squared, if someone asks for these two, as the value of x is increasing, I will see that the e to the power of x keeps growing and growing. So it's an increasing function. That is one more word which we use. When we use the word called increasing function, as x is increasing, we see that the e to the power of x value keeps increasing. First aspect. Second, this value can never become negative. As you are seeing that as x is decreasing and decreasing, the value of e to the power of x is just coming closer to 0, but it's not becoming below 0, which means it can never be negative. E to the power of x can never be negative, but it can only be approaching 0. So the other way of writing this is, as x tends to minus infinite, e to the power of x tends to 0. This is one way you can express the relationship between x and e to the power of x. And the where does it cut? Whenever we talk about graphs, another important thing that we need to understand is at what points does this particular graph cut the x-axis as well as y-axis. We have already understood that this graph cannot cut the x-axis. it, because it approaches 0 but it cannot become negative. Only when a particular value becomes negative and positive, only when both the signs are available for that particular value, then only it will cut the x-axis. But in this case, e to the power of x is always positive. At the worst case, it can come down to 0, which means e to the power of x can never be negative, and also it does not cut the x-axis at all. Whereas at the y-axis, it always cuts at the point x equal to 0, and the value correspondingly is 1, which means I can very well write a special case e to the power of 0 equal to 1. That's one more property we need to understand. And now that we are talking about e to the power of x, actually speaking, it's a special case of a generalized form called a to the power of x, where a is any positive number. Any positive number. So e is also a positive number, right? E is nothing but 2.718. So e is a special case of a to the power of x. Now, so the typical a to the power of x graph will be like this only, just like your e to the power of x, and where it will be cutting your y-axis at 0. As the value of x keeps increasing, a to the power of x keeps increasing. As long as a is a positive and greater than 1, it is an increasing function as long as a is greater than 1. Now that e is 2.718 and it is greater than 1, we see that the e to the power of x is also an increasing function. But otherwise, any general function of the form a to the power of x, where a is a constant and is greater than 1, we see that the graph will be more or less similar to that of e to the power of x, in the sense it's an increasing function. But if you see that a is less than 1, which means a lies between 0 and 1, because we are talking of one side a being a positive number. So if a lies between 0 and 1, we see that it is a decreasing function. What does a decreasing function do for us? As x is increasing, a to the power of x keeps falling and falling and falling, and probably it approaches 0. Whereas as x is decreasing and decreasing, we see that the a to the power of x is actually growing. So one thing we have to understand in the case of a to the power of x is, if a is greater than 0, we see that it is an increasing function. If a is less than 0, we see that it is a decreasing function. One aspect. Second, both these a power x, whether it is greater than 0 or less than 0, they intersect the y-axis at the point 1. And we also see that e to the power of x is a special case of a to the power of x, especially an increasing function, because e value is 2.718, whereas if a is greater than 1, we have seen that the function is an increasing function itself. So these are some of the most common points you need to be comfortable with if you have to solve some of the questions relating to the exponential function. Now we'll move on to our next function in this analysis, which is the logarithmic function. Yes, in logarithmic function, there are 3 variants. One is represented by log, log, and the other is represented by ln. ln means natural logarithm, which is the most common version of the logarithms which we use, whereas log is called as a common, or the name is common, But the most heavily used logarithm for all our finance related calculations is natural logarithm ln. Even in your calculators you see these two symbols, log as well as ln. Ln is a natural logarithm, log is a common logarithm, and for a lot of calculations we depend on natural logarithm. The difference between the two is the first one uses 10 as the base, number 10 as the base, whereas the natural logarithm uses e as the base. E is exponential function as a base. Exponential e is 2.718. 2.718 is used as a base for the natural logarithm, whereas 10 is the base used for common logarithm. But yes, whatever is the base that we are talking of, whether it is natural or common, as far as this particular graph shape is concerned, we are not much bothered. Log 1, whether it is log1 or ln1, both of them will be equal to 0, which means at the point 1, the graph will cut the x-axis, and the logarithms are defined only for positive values. So they are not defined for 0 and negative values. So corresponding to x equal to 0, there is no value for the logarithm at all. There is no value for logarithm, so that's the reason you can't find. Even this particular graph will tend to minus infinite, but it will not touch the y-axis at all at 0. If it touches, means for x equal to 0, that is the value of y. So we find that the log x graph does not touch the y-axis at all, but it goes very close to y-axis, which means as x tends to 0, log x, whether it is ln or log, tends to minus infinite. This is one more observation for us from the log. And what we are seeing is, as the values of x are increasing, log x is also keeping on increasing, which means it is an increasing function. Fair enough. So when someone is giving you a graph, 4 different graphs as multiple choice answers, and asking you to select which one represents what, I suggest that you immediately substitute few values. Let's say 1, 2. So from 1 to 2, if the value is increasing, then I'll say that it's an increasing function. So my graph should look more like an increasing function graph out of the various options. Otherwise, it should look like a decreasing function kind of a graph. So here, yes, it is an increasing function. Logarithms are not defined for negative values. Log 1 is always 0. And yeah, as x values are increasing, the log x value is also keeping on increasing. And you will understand slightly at a later point in time, the logarithm function ln is the inverse of e to the power of x. Log x function is the inverse of e to the power of x. When we talk about inverse functions at a later point, we'll try to understand what I am meaning by this statement, but for comfort level, try to understand this statement. Log x is an inverse function of e to the power of x and vice versa. So these are some of the things you need to be comfortable as you are going to use the log function. All right. Let's move on to the next important function in our space. We will talk about the power function y equal to x power n. So y equal to x to the power of n, like x squared and x cubed. So we have two different kinds of shapes, especially one when n is even, the power. If the power is even, we have one kind of a shape which is more like this, because even powers, the values can never be negative. The values are only positive. So that's the reason what you are seeing is, you will find all the values above the x-axis only, no value below the x-axis, especially for even powers. And you also see that the graph will be symmetrical about the y-axis, because whether you have x value as 1 or minus 1, it hardly matters. Minus 1 to the power of even number is always same as plus 1 to the power of even number. So you will always find when n is an even positive number, you will find that it's a mirror reflection over the y-axis. And especially when you find things like that, we call such kind of function as even function, which means if f of minus x is same as f of x, which means the value corresponding to all negative values of x, if it is the same as their corresponding positive values of x, then such function is called as even function. So you can try out, let's say, on random basis, f of minus 3. Find out what is minus 3 squared, 9, plus 3 squared, 9. Both of them are same. That is when I call that particular function as an even function. And whenever we find an even function, that graph of that function will always be a symmetrical around the y-axis itself. So when n is an even value in x power n, we see that the graph will be symmetrical about the x-axis, and we call such kind of function as an even function. But if n is odd, like x cube, x power 5, when n is odd, what we will typically see is it is nowhere symmetrical about y-axis, because all positive as well as negative values are possible. And simply put, if x is positive, x cube is also positive, and x is negative, x cube is also negative. So x cube will observe the same behavior as x. So all odd powers will have the same sign as the original x itself. So you will find some level of symmetry, but not across the y-axis, around the y-axis. But you will find typically a symmetry existing around the y equal to x kind of a line. Probably if you see here, if I draw a 45-degree line like this, or some degree line, so I see some kind of a symmetry like this across this line. So that is the kind of symmetry I can observe, but not across the y-axis. And these kind of functions, I call them as odd. What does that mean is, if I try to find out the value for a negative value, if it comes exactly same as its corresponding positive value, but just a sign difference, minus f of x, we call such kind of functions as odd functions. Let's say minus 2 cube, which is minus 8. Whereas if I take 2 cube, it is plus 8. The value is same, but only the sign is different. Then we call them as odd functions. So we need to be very comfortable between the graphs of even versus odd functions, especially when we are talking about the power. Because if the power is an even number, we end up with an even function, and we see that even function is symmetrical about the y-axis. If the power is odd, we see that it will be an odd function, and the odd function will not be symmetrical about the y-axis. And some more things about the power, because in the earlier two cases we have seen that n, which the power we are talking of only in terms of positive integers, which is natural numbers. Positive natural odd natural numbers means the graph of this form. Even natural numbers means the graph of this form. But they can still be negative numbers, negative integers. If n is a negative number, just like n is a positive number, we see the graphs. But the only difference is, instead of a continuity there, we will find a discontinuous. So if n is still even, like x to the power of, so I want to talk about x to the power of minus 4 versus x to the power of minus 3. This is typical x to the power of minus 3, especially when we are talking about n being positive, we got x to the power of minus 3 more like this. So positive odd number means we see that it is continuous like this and cutting at x equal to 0. Whereas when we talk about x is a negative but still odd, we will find that the graph will be more of a decreasing function, because x to the power of minus 3 is nothing but 1 by x cube as per the formulas. So 1 by that, if one number is increasing function, the 1 by of it, which is the reciprocal of it, will always be a decreasing function. So what we typically see is, right from here you see that there is a decreasing function, and as x tends to infinite, this x to the power of minus n will tend close to 0. So it will be both on positive as well as the negative side. A similar kind of an approach is seen when n is a negative odd number, whereas if n is a positive negative even number, we see a similar kind of shape. This side remains the same, whereas instead of in this quadrant, we see the graph more in this quadrant, more symmetrical about the y-axis, but it would be more in terms of this, especially for x to the power of minus 4 or x to the power of minus 2 kind of shapes. Whereas if it is for positive integers, we see it, whereas if it is for odd negative integers, we see that it will be symmetrical across the diagonal but not across the y-axis. Now the fourth scenario is, what if we are talking about n which is not an integer, the power is not an integer, but it's like a square root, which is like 0.5 kind of stuff. What we will typically observe is, this becomes an increasing function as x increases, and because the square root is not defined for negative numbers, we see that we will not find anything for negative values of x. So the x is only from 0 and onwards. We don't find anything for the negative values of x, only for the positive values. And what we are also seeing is, as x is increasing, the square root of x is also keeping on increasing. So this is also a kind of an increasing function. So we have to be very comfortable in using these various power kind of formulas and trying to understand the shape of these kind of graphs, because once we know what is the pattern in which these particular shapes keep moving, we can make the appropriate transformations and we can use them in the way which we typically want. Then the next function which we all need to be comfortable with is the modulus function, which is denoted by mod x. Mod x is whatever the x is inside, the output will always be a positive value, which means mod minus 3 is also equal to 3 and mod 3 is also equal to 3. Whatever is the value inside the modulus, the output of it is always a positive value. The negative sign is ignored in case of modulus function. So that's the reason we even call a modulus function as the absolute value of x. We ignore the sign of x and we present only the absolute value. So when I say mod x equal to 3, it means x could have been either 3 or even minus 3 also. Because mod minus 3 also is equal to 3. Mod 3 is also equal to 3. So whenever someone makes a statement mod x equal to 3, then x is actually having two possible values, minus 3 as well as plus 3. And the similar way, when someone makes a statement mod x is less than 3, it means probably I should look at it as x lies between minus 3 and 3. Simple way for you to remember. Whenever we talk about mod x is less than 3, you can very well assume that x lies between minus 3 and 3. And if someone says mod x is greater than 3, I say that x does not lie between minus 3 and 3. It is below minus 3 or it could be above plus 3. So we have to be comfortable in terms of solving for the expressions given with a modulus sign, convert them into a non-modulus. For example, okay, I have a question saying mod 3x plus 5 is less than 4. So what does this mean for me? Either 3x, so a simple way for me is 3x plus 5 lies between minus 4 and plus 4. So I will write this as minus 4 less than 3x plus 5 less than plus 4. So I can write them as two in equation. 3x plus 5 is greater than minus 4 is one thing. 3x plus 5 is less than plus 4 is one thing. Now if I try to solve this, 3x is greater than minus 9, which means x is greater than minus 3 here. And here I can write it as 3x less than minus 1 and x less than minus 1 by 3. So x is greater than minus 3. X is less than minus 1 by 3. So I can say x lies between minus 3 to minus 1 by 3. And does it include minus 3 and minus 1 by 3? No. So the brackets will tell, because if it has been less than or equal to, then all these would have become less than or equal to, which means even the minus 3 should be included and minus 1 by 3 should be included. So the brackets will decide whether I am including them or not including them. If I show with a plain bracket like this, it means both minus 3 and minus 1 by 3 are excluded. But if I represent with a square bracket like this, then it means minus 3 as well as minus 1 by 3, both of them are included. Sometimes people write like this, minus 3 minus 1 by 3, which means here, because square is associated only with the first one, then I'll say minus 3 is included in the solution but not minus 1 by 3. So the brackets, depending on whether you are representing them as a plain bracket or a square bracket, whether you are including that particular value as a part of the solution or not including is what will actually come out. So this is the way you solve any modular specific problem. And for mod x, the graph will be typically like a V shape. Again, it's a symmetrical about the y-axis. This is 0. Symmetrical about the y-axis means it's an even function, as we have discussed earlier, right? And also it can never be negative, because we are only bothered about the absolute value of x. So this is always a positive value. and as x keeps increasing, mod x value also keeps increasing. So these are some of the things we have to be comfortable with when we are trying to solve the modulus x related calculations, right? So now let's move on to the next important function, which is the integer function. Integer function is represented with a square bracket of x. So if I'm talking about a value integer function 3.2, then it is nothing but 3. So we are trying to find out the integer part of it. That's it. So even for 3.7, the integer value is 3. It's not rounding. Try to understand the difference between the two. It's not rounding here. Probably look at it always as the lesser side of it, right? 3.7, the lesser side, the immediate integer on the lesser side, it is 3, right? Then how about minus 2.3? Don't get confused here. This is not minus 2. The reason is minus 2 is greater than minus 2.3. I'm making a definition that the integer value is always the one which is on the lesser side of that. So for negative numbers, please be careful while using it. This is minus 3. This is always on the lower side. So take the integer function always as the value on the lesser side, the nearest integer on the lesser side. That is what we are defining as integer function. So ignore the decimals. Only in case of positive, it is straightforward. Just ignore the decimal, you will get the integer function value. Whereas for negative numbers, please make sure that you are taking the other side. So if I try to, you are taking the next on the lower side. So the graph for it, it is more like this. If you have, let's say 0, 1, 2, 3, any number that is lying between 0 and 1, the integer value will be 0 itself. So this is a line like this. For 1 and 2, it is always 1 only. For any number between 2 and 3, this is always 2. For any number between minus 1 and 0, this is always minus 1. So what we are looking at is the graph of integer function is like steps. So that's where we call it as a step function. So these are some of the things you have to be comfortable with when we are dealing with the integer function. And then we also will deal with the max and minimum values. Max is out of all the possible values in a group or a set, which is the maximum value and which is the minimum value. It's a straightforward. Let's say if I'm talking about what is the maximum of x minus 2 comma 10 in the region 0 less than or equal to x less than or equal to 20, which is also means x lies between 0 and 20. What is the maximum of x minus 2 and 10? Now you see, if x equal to 3, just 3 minus 2 and 10. So maximum of 1 comma 10, definitely it is 10 only. And similarly, let's say if x is 10, then it is maximum of 8 comma 10, which is still 10 only. So how long? Until x equal to 12. If x equal to 12, also maximum of 10 comma 10, which is still 10. But think of x equal to 13. So right from 0 to 12, I see that the value is equal to 10. But if x equal to 13, so it becomes maximum of 11 comma 10, which means it is 11. So how do I sketch the graph for it? Up to 12, up to x equal to 12, the value is 10 only. The maximum is 10 only. So let's say 1, 2, 3. Let's say here I put 12, 13, like this. So up to 12, right from 0, the value is 10. But after that, I see that the value becomes 11, 12, 13, and so on. So this would be the graph associated with max x minus 2 to 10 for the region 0 less than or equal to x less than or equal to 20. So it's nothing but you are substituting the values, and based on them you are doing the appropriate calculation. And one more thing you have to be comfortable with is, in this chapter, as we have discussed right in the beginning, in the expansion of e power x, we have discussed about the n factorial, which is applicable for n being a natural number itself, multiplication of all those numbers up to 1. That is what is given as a factorial value. So what you could very well write it iteratively is n factorial, because this is nothing but n into n minus 1 into n minus 2 into so on up to 1. Probably this is nothing but n minus 1 factorial. So you could very well write it as n into n minus 1 factorial is same as n factorial. So that's the one more way you can write it in an iterative fashion. So again, n minus 1 factorial you could very well write up to here as n minus 2 factorial. So n into n minus 1 into n minus 2 factorial. Even these kind of expressions can be derived from the value, from the formula of n factorial. So this is one common thing you have to be comfortable with. The calculations involving the factorial is one more thing you have to be comfortable with. And I also suggest that the comfort should be there with respect to a function called gamma function, or find out the value of gamma. You don't need to bother too much about the integral aspect of it or the technical aspect of it right now, because most of the questions which would be involved for you in the computation of gamma is find the value of a particular gamma. So let's say I want gamma 3. Always write it as, so the general form is gamma x minus 1 or gamma x is equal to x minus 1 gamma x minus 1. So this becomes x minus 1 and gamma x minus 1, applying the same formula, x minus 2 gamma x minus 2. Now what you are seeing here, x minus 1 into x minus 2 into x minus 3, that's how it goes. So it actually goes like an x minus 1 factorial itself, if we are talking of x being a natural number. If x is an, so some of the things I can very well talk about here, the questions that can generally come out for you with respect to gamma. Gamma of x is equal to x minus 1 factorial if x is natural number. But if x is a not natural number, the only thing we have in our scenarios is for 0.5 related stuff. Let's say gamma of 3.5. How do I write it? I use it the original notation. X minus 1 into gamma x minus 1. 2.5 into gamma 2.5. Now if I expand it, 2.5 into 1.5 into gamma 0.5. That is where the last step comes. Wherever you end up with gamma 0.5, you can very well take the expansion of gamma 0.5 as square root of pi, which you can write it as 2.5 into 1.5 into square root of pi. Pi is nothing but 3.14. You have made it as a mathematical constant earlier. So gamma root of pi, you multiply this, you will get your gamma value. So typically the calculations as far as this chapter is concerned, or this subject is concerned for you, is either they would directly ask for the calculation of factorial, or a gamma, which is again very much linked with the factorial itself to some extent, especially if n is if the x is an integer, then it is very much linked with the factorial. But if it is not an integer, then you can do something like this. x minus 1 into gamma x minus 1. Repeat the process in an iterative fashion and try to get out for your value of gamma. Finally, if it comes out as gamma of 0.5, you can make an approximation of equal to square root of pi itself. And this chapter also ends up with if n is very large, n factorial is difficult to find. Let's say probably 40 factorial, right? You can have your calculator to find that out, but if you have manually doing it 40 into 39 into 38 into so on, it's not that easy to find out the value of 40 factorial. So that's where they have brought in some kind of an approximation. So that is called as a Stirling approximation. There is no big proof. Proof is out of our scope right now. So I can very well look at it like 40 factorial is nothing but 40 to the power of 40 plus half, which is 40.5 into e to the power of minus 40 into square root of 2 pi. That is what will come out as 40 factorial. And if the question is about gamma 40, it comes just simple like 40 to the power of 39.5 is same e to the power of minus 40 into square root of 2 pi. Because all we know is gamma of x is x minus 1 factorial only. Gamma of x is x minus 1 factorial, right? So divide both sides by x factorial, which is nothing but 1 by x. Gamma of x by x factorial is equal to 1 by x. So even here also it should come out as 1 by 40. So that's the reason this approximation also will work for us in some of the cases. But yes, you don't need to bother too much into the approximation part as long as you are using the calculator. If the factorial symbol is present in the calculator, no harm. But if it is not present on your calculator, then this is one more way of arriving at your approximation. And in some of the cases, probably if the question asks about gamma, the better scenario is what is the value of gamma 38.2. That is one of the places where I suggest you use the Stirling approximation. 38.2 to the power, the 38.2 minus half, which is 37.5 into e to the power of minus 38.2 into square root of 2 pi. Use this approximation to find out the gamma 38.2 in case a question of that kind arises. Using the Stirling approximation, you can very well identify this formula and you can very well display your answer. So that is one way you should try to use this particular concept. So this is what is typically covered for you as a part of the standard function. So if you try to revise quickly what is being covered, we have to understand thoroughly the formulas of the graphs, shapes and properties of e to the power of x, log x, and the power function x power n for positive odd power, positive even power, negative odd power, negative even power, and even a fraction kind of a power. And we have also looked at understanding the function of modulus of x, integer function of x, maximum and minimum of x, and even the factorial and gamma function. So you have to be comfortable with all these calculations to get a decent hold of scoring in these particular exam. If you have any doubts as far as these concepts are concerned, I request you to feel free to give me a call on this number 919848012123. You can also drop in an email to me at my address vamsidhar@pacegurus.com. I suggest you to visit the website www.pacegurus.com for all our further updates regarding the training and consulting programs we do in the areas of finance, analytics and actuarial sciences using the tools like Excel, SPSS, VBA, etc. I hope this session has given you a lot of insight into the preparation for your ASET exam. We welcome your valuable feedback regarding this and improving this curriculum. Thanks a lot for listening to this session. Thank you very much.